Hello there, my name is Charles Sipa. Welcome to a presentation which I've entitled here, The Real Number System. My intention here is to sort of recap some important ideas about numbers so that we can have a quite good working understanding of real numbers as you explore your calculus course. So I would like to start in the following manner. I think one of the numbers or the type of numbers we first encounter in a very natural way is what we call natural numbers. Like, for example, we quickly get aware of a concept of a quantity to answer questions like how many. Like, for example, if somebody would ask you how many suns do you have, sun as in sun, we know that we've got only one sun and you've got only one moon. And then that basically takes us to counting. In this case, like we can have this, looking at this picture, we can count that we've got one red triangle here, two brown ones, three, and so on. So that takes us to a set of numbers. I use the word set here. In this case here, I would like to understand the set as a kind of a vessel or a collection of certain objects, maybe which are linked together by a certain property. Like, for example, in this case here, we're talking about natural numbers, set 1, 2, and 3. Then you've got a set of natural numbers which can represent geometrical this way. What is important here is that you should see that a set of natural numbers is actually a kind of a sequence. Once you've got one, you can actually sort of do a process of accumulation, get another one, then you've got two, get another one, you've got three. Simply what I'm saying, if I've got a number, I'll use n here for a number which is a natural number. We will always have another number which is n plus 1, which is, we can say in the sequence, that is the successor of n. And the number before n plus 1 will be n. And you can see that in the set of natural numbers, there's no number before 1. So number is sort of the first, 1 is the first special number which you use to generate the rest of the numbers. So talking about set, we should also have a good idea of what we call an empty set. An empty set is denoted by this symbol. Like already, if we look at this number, representation of numbers here, we can see that there's no natural number between 1 and 2. No, between 2 and 3. So if we talk about a natural number between a number and a successor, basically then we'll be talking about an empty set, a set or a vessel which does not contain anything. In this case here, if we to count the number of elements in the set, we'll see that there are no elements. And then that takes us to another idea of having a symbol which indicates the absence of elements. The set of natural numbers will be symbolized by this n written this way. And of course, the word tallying here, it refers to the count of counting. Like if we were to count the yellow, let's say these yellow squares here, we basically would tally them with a quantity like this. Say one stroke for this one stroke for the next one, and one stroke for this one, and then we end up saying the number of the yellow squares here are 3. That is called tallying. That's actually the early type of counting people used to keep their quantities of maybe whatever they have. Maybe it's a head of cake or whatever. Now talking about the element sets and the number of elements in the empty sets, we know that there's nothing. This takes us to another concept of what we call whole numbers. And actually, we all know that in the set of natural numbers, we can add numbers, like we can say 2 plus 1 to get 3. We can also do operation of subtraction, which is 2 minus 1, which will get us 1. And then if we do an operation of 2 minus 2, in other words, if we're given a set of, let's say 2 oranges, you take away all of them or eat away all of them, we remain with nothing, then you can say we remain with 0. So this is the symbol which I'll put here. which indicates the absence of quantity. In this case, we say that a set, empty set has got 0 elements, meaning it has no elements. So then this gives us the set of whole numbers. What is important about the set of whole numbers, you can see here, we can do addition basically in an unlimited way. Any two natural numbers we pick, we can add them, we're going to get another natural numbers. And also, you already used the habit of using letters for numbers. For example, if you are picking a natural number, let's say x plus another natural number y, we know that this result is always going to be a natural number, or in this case, in the set of whole numbers, that will be also a whole number. But we must notice that if we were to do a subtraction and say x minus y, this we cannot guarantee that this is a whole number, because subtraction is done in a limited way here. It can only be done in this case when x lies on the right of y, meaning that x is greater than y. So we can do that. So in this case, greater or equal. If equal, then we get this kind of situation, we get 0. If not, then we get a whole number. So in this case here, subtraction is kind of limited there. So again here, addition, like we said, can be done in a limited way. If we add a number, the same number, repeatedly, this gets us to another operation which we call multiplication. In this case here, we'll say we've got 3 of the x's, which actually what this means is simple. We know that if you say 3x, 3 is the coefficient, x is and then the variable here, then we say this actually means that 3 times x, which similar repeated addition of the same thing. So once we've multiplication, like for example, if we take 2 plus 2 plus 2 plus 2, that will be a repeated addition of 2, which would say is 4 times 2, which you can see here again that if we take this in this way, that will be 4 here plus 4, and then this will take us to 2 times 4, which lends us the fact that if we've got two numbers, x and y, if you multiply x by y, it's the same thing as multiplying y by x. Then we say the multiplication is commutative. And now that is repeated addition. Now once we've got repeated addition, we can think of also repeated multiplication of the same factor. For example, if we now multiply 4 by 4, that is now repeated multiplication of the same factor. This we normally write as 4 squared. And then notice the difference here. If we had 4 plus 4, then you would have here 2 times 4. So you can see here what I'm trying to tell you here. Addition can be abbreviated by the process of multiplication, whilst multiplication can be abbreviated by this process which we call exponentiation, which means multiplying the same factor by itself. That is exponentiation. And in terms of numbers, you need to know all these rules of exponents and so on. And in multiplication, again, you need for us to know your multiplication very well, how you do it, maybe number of 1 digits or more digits and so on, multiplication of decimal numbers when you get there. Also, that will be very, very, very important. So this will be multiplication. So multiplication is kind of an abbreviation of addition, and the exponentiation abbreviation of multiplication. Because just check that if you had to multiply let's say 4 10 times, you would multiply 4 times 4 and so on times 4. Then instead of writing this factor 10 times, you will simply say 4 to the power 10. So that's why I'm saying that that's the abbreviation. Same thing happens to addition. If you have 4 plus 4 plus 4 all that 10 times, then we write that the symbol as 4, 10 times 4. Important now, you should see how the 10, the role is playing here in its position, and here is a different position, and then it gives a different meaning. That is very important. Now, in talking about whole numbers, so it also is important to note that in the set of whole numbers, we can have subfamilies of whole number. Like, for example, we can talk of even numbers. Even numbers, I think it's important to know the general notation of even numbers in this case. Like, for example, if we say n is a whole number or even a natural number, so an even number will be any number m, which is 2 times n being a member of that. So which basically means that this number is a multiple of 2. And then we also have got what we call odd numbers. In this case, even numbers, we can think of 0, 2 times 0 is 0, then 2 times 1 is 2, 2 times 2, 4. So these even numbers are simply 0, 2, 4, 6, and so on. And then we've got odd numbers. Odd numbers in this case are numbers like 1, like 3, like 5. If you look at them carefully, for example, looking at 1, we'll see that the 1 is 2 times 0 plus 1, whilst 3, this would give 1, whilst 3 will be 2 times 1 plus 1, and then 5 will be 2 times 2 plus 1, then that will be 5. Then even numbers in general, then you must notice that they are going to be denoted in the following manner: 2n plus 1. That is the notation of an odd number. So very important to know that. Then this is odd number and that is even number. So that is important to know about that. So even numbers, basically the numbers which we know they are divisible by 2, but odd numbers they will be divisible by 2, but with giving a remainder of 1. That is very important. Okay, so the next thing, next numbers which we like, or the next system of numbers which we have come as a solution, or we get that set as, like we said here, we said subtraction is limited. In other words, in this set we cannot do things like 9 minus 10. We cannot do 11 minus 12. That gives us that takes us to another idea of that if we have numbers on the number line like this, then maybe we can find a solution to this number using the number line, knowing that we're not doing addition here. What do? You say 2 plus 3, and then you have the section on the number line here by starting at 2, saying 0, then 1, 2, 3. Then you can say the answer here is 5. And then if you are subtracting, if you say 6 minus 2, what you do, you start at 6, now moving in the opposite direction, in this case towards the left, and say 1, 2, then you say your answer is 4. Now, taking cue from this kind of practice, we can think of how we can do something like this. We started at 9 here, and go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, before we say 10, we're aware that if we were to make 10 this step, we will be somewhere there. Then this takes us that if addition and subtraction could be done this way through a number line, maybe then the answer of this calculation must maybe lie somewhere there on the left of 0. So This takes us to numbers called integers, which are very easy to construct. Like, for example, looking at a number 1 here as a difference of 8 minus 9. Sorry, 8 minus 7, sorry, and 9 minus 8, and even 10 minus 9. So if we then do that kind of say this is a difference, and we know that in nature symmetry manifests itself very easily. Like, for example, going doing 9 minus 10, we saw that it takes us beyond there. So all that we can do, we can just do a simple construction which we base on symmetry, and then take this, transport this, this one here on the other side using symmetry in such a way that we get a point here which is also at the same distance like 1 there. Then if we do that and get a mirror image of this, then here it says we're going to have 9 minus 10. If you look at the mirror here, stand in front of the mirror, stretch your hand towards the mirror, you will see that your hand is nearer to the mirror than your back, so the image also will have exactly the same thing there. This 10 is a mirror image of that, minus is a mirror image of minus, and 9 is that. Then we get this kind of problem, then which means the answer is there. So exploiting that kind of idea, you will see that we are able to extend the number line this way, whereby on the left of 0 we've got 1, 2, 3, 4, 5, but to indicate that it's on the left, we just use a minus sign there. Then we end up with a set of what we call integers, which will denote this way. And in this case, we have here numbers which are 0. 0 is not on the left of 0, or it's not on the right of 0, so it's not positive nor negative, so we put 0 there. Then we've got a positive 1 and a minus 1, and a positive 2 and a negative 2. That takes us to a kind of a number line which is symmetric, and we call those integers. That's the thing. And then if you think of these numbers now with the negative numbers and so on, then you can talk of temperatures like -1 and so on, and then all these exercises now can be solved. Then the answer here is becomes -1. All that took us to learning how to operate with numbers with different signs, like, for example, adding -7 to 5, and even adding 6 to -4, which is the same thing as subtracting 4 from 6. So they will learn to operate with the integers. So that takes us also to, even when you're multiplying, we can multiply 2 times -2, and then we learn how to combine signs in multiplication and so on. Then it takes us to rules of combination of sign, like a -1 times plus, let's say minus times plus will give you a minus times a minus will give you a plus, and a plus times a plus will give you again a plus. Then we get to a concrete idea that whenever we're multiplying now signs which are different, we get a negative sign, but when we multiply in the two numbers with same sign, we get a positive sign. So it's important also to recognize that. So then now, if we're in this with integers and so on, you will notice that if we now, like, we understood that 2 times 4 is equals to 8, then we have problems of this nature which you did at school, like 2 times box equals to 8, which you call equations, and then later we'll write the same equation as 2 times x equals to 8. And then this type of equation, you can see that you can calculate it and say x is 8 divided by 2, and you get a 4, which is a whole number, which is an integer, which is a natural number. But what we know is that this kind of equation in the set of whole numbers, in the set of integers and natural numbers, does not always have a solution. I mean, this type of equation, for example, if we had here 2x equals to 5, and obviously if we try to do this kind of a thing here, we would get something like x, which is equals to 5 over 2, which is not something which is an integer, and it's not a natural number, and it's not a whole number. And then that's basically takes us to the need that we maybe need to have more numbers or a richer set of numbers to address solutions to these types of equation. And that takes us precisely to numbers we call rational numbers. Rational, basically we could say the rational associate that with a ratio. So then there we can just start by looking closely at this whole. We can say this is one whole, but you can see that this whole is made of many different parts. So if we take, let's say, this 1, 2, 3, 4, we'll say we've taken 4 parts out of this 1, 2, 3, 4, 5, 6, 7, 8, and 1, 2, 3, 4. And then here we've got this what we got here is 32. So we've got 4 parts out of 32. That takes us, you can say 4:32, which gives us a ratio. And then this kind of a quantity would be called a rational number. So when we get here, this is actually using this kind of layout, we actually get to notice that the multiplication is actually a kind of a 2-dimension operation. We have to move in this direction and move in that direction. Then you get this kind of a 2-dimension surface, and that is important for multiplication. You must look at it as an operation which is 2-dimensional. I'll show it now when we try to multiply fractions. So now what we need to have here, we know here, we need to know, okay, how we add rational numbers like this. We know that we find a common denominator, which basically will be number which is divided by the 2 denominators, to say b, d here. Then we divide this by b by saying bd divided by b. Then we simplify this to 1 and multiply that by the answer by a. Then you get a d plus then d divided by d dividing bd, you get b, and then you get here plus c. So addition of that is not important. So what I want to illustrate here and make sure say that you understand how we multiply fractions is the following. Like I said, now we take out multiplication as a 2-dimension kind of thing. Now check that if I go this way along this line, if I stop somewhere here, I would have taken, let's say, 2 out of 4, something which you can simplify by and get half that thing. And if I go this way, here we've got 1, 2, 3, 4, 5, 6, 7, 8. So if I were to go up to this point here along this line, I would have got 1, 2, 3, 4, 5. This will give us 5 out of 8. Now if I take this 2-dimensional portion here of 5 out of 8 by 1 out of 2, I'll be saying basically I'm multiplying 1 out of 2 multiplied by 5 out of 8. So if I want to know how much do I have out of the whole square here, what would happen actually is I would take this block up to there, which means then out of the 2 I would have taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which means this will be 10 out of 32. Now if you look at 10 out of 32, 10 is actually 2 times 5, and here this will be 2 times 16. And then when we do that, then we can simplify this and that, and then this gives us 5 out of 16, which is simple, looks like this 1 times 5 over 2 times 8. For that reason, that's why when we multiply fractions, we simply say we multiply the numerators alone and multiply the denominators alone. and that should mislead you when you are doing your addition. That you cannot do when you are doing addition. It's only when you are multiplying, you just operate with the numerators and separately operate with the denominators, you get a denominator. With numerators, you get a numerator. And then I'm going to talk about the divisions of fractions later when we've got other things, very important things about the numbers. That's it. Then, but what is important here is that already we must be now aware of the fact that when you multiply 1 by any number a, we simply get a. That is important. So then we're now talking about rational numbers which we're going to denote by this sign for rational numbers. And then we know what we see now is that we've just seen that a rational number is a number with this kind of structure where there's a numerator and a denominator. And then this is a set of numbers. Rational is P over Q, and such that P and Q are integers with, in this case with Q always different from 0, because we cannot divide by 0. I'll try later maybe in discussion to convince you why you cannot divide by 0. Actually is something of this nature, like a number a which is not 0 divided by 0, or 0 over 0 itself. They are considered as undefined entities. You can never give an answer to a calculation in this way. So we just call these undefined entities or indeterminate forms. That's what sometimes people use. So, but important here, you must know that rational numbers are like this. What we know, we have to know, we know how to add them, we know how to multiply them. Well, I'll talk about addition later and trying to explain exactly how it's done. Maybe before we go very far, let's treat division here already. Most important is that we know that a number multiplied by 1 is 1, and we call 1 the identity of multiplication. Now, if now we're to divide, let's say A over B divided by C over D. The most important things we can take advantage of this fact that 1 multiplied by any number is, and also that A divided by 1 is equals to A. This is very important. So in other words, we're saying here, the easiest number to multiply with is 1, and the easiest number to divide it is 1. So whenever we were to do division, we would wish to divide by 1 because it's the easiest thing we do. We know the answer before we start the division, and then that's two things we need to know when we're going to understand how this works. The next thing is, if we see that we've already done it here. We see that if we have a fraction like 5 over 16, if we do this multiplication, let's say we multiply by 2 over 2, it's like we're multiplying by 1. Because of this, we're still going to get this answer. But we can look at this also as 10 over 32. So that does not change that does not change the fraction. So that's exactly what we're going to use here. So which means given any fraction, if you given any fraction, you multiply its numerator and denominator by the same number, you still get the same fraction. This takes us to this. If I've got A divided by B, which is the numerator, this fraction divided by C over D, then I can say I wish I were multiplying dividing by 1, then I will know the answer. But because of this, what we're going to do here, because of this, what we're going to do here, we're going to try to multiply the numerator and the denominator by the same number. But in this case now, the number we're going to take is the following number. I think just before we get there, let's understand one thing here. If we've got 2, as a rational number, we must understand that 2 is a 2 over 1. This is equals to 2. Now, if I look at 2 in relationship to a number like half, I can just simply say I've swapped around the numerator and denominator to get half. And then I'll call this half inverted 2. So half is inverted 2. And then notice that now, if I take this inverted 2 and multiply by 2, I'll be doing 2 over 1 multiplied by 1 over 2. Then if we follow the multiplication of fractions which we've just learned here, we'll simply multiply 1 times let's say 1 times 2 in the numerator, and also 1 times 2 in the denominator, and then that gives us 2 over 2, and then that gives us 1. So which means as long as I've got a number x which is not equal to 0, because already I said this cannot be done with 0, then there will be another number which I can call 1 over x, which is called reciprocal, such that when I multiply x by 1 over x, this gives us 1. And then this idea is the one which is going to help us here. 3 ideas are going to help. This idea of 1 times that equals to a. 1 divided by that equals to a. The expansion of fractions, that. So I want to do that here. So what I'm going to do now, already from this we know that if I have got c over d, and I get another number which I call inverted c over d, that will be d over c. And if I multiply the two, I get 1. So what that's going to do, I'm going to use this here to convert the number which is dividing it to be 1. So what I'm going to do here, I'm going to say a over b divided by c over d multiplied by d over c. I'm now doing this kind of expansion, multiplying the denominator. I've multiplied the denominator here, the divisor. So I should do exactly the same thing, multiply the numerator by the factor d over c. And then having done that, then using this, we see that this gives us 1. Then we remain here with a over b multiplied by d over c divided by 1 from there. And then coming to this, we get the answer as a times d over b times c. This is what we were told at school, that if you are dividing fractions, simply invert and then multiply. Because if you want to look at what has happened here, you will see that this fraction has been inverted and multiplied. So that is the division of fractions. That is important to know. So now, once you've got rational numbers, which of course we should notice that the integers like 2, they are rational numbers by taking them with denominator 1. So what do I mean here? I mean natural numbers are rational. Whole numbers are also rational. The integers which contain rational are also rational. Since a minus 4, we can simply take it as minus 4 over 1, or even as 4 over minus 1. That's the thing. So now, which means then the set of integers is contained in the set of rational numbers. Then if we've got a number line like this, so we can see that we can also think of a half there as a number on a number line. A minus half similarly is a number on a number line. So in other words, now we can say this line here is packed with rational numbers. All the whole numbers we had before, the natural numbers, the integers, are rational numbers, and we've got more rational numbers like this. Then at this stage, then you can take an equation of this nature and say this is an equation whereby x is a number 5 over 2, which belongs to the set of rational numbers. And then at that stage, one can have the impression that all the points of the line here are numbers, some of them being integers, whole numbers, and some of them real rational numbers with a kind of numerator and denominator which is not equals to 1. But that is not all. Not all the points of this number have been taken by rational numbers. We must understand one thing here, that rational numbers are dense. In other words, they are highly densely populated on the number line. What do I mean like that? For example, let's say 1 can be written as 6 over 6 as a rational number. So if I go to 1 just say step 1 leap here from 0 to 1, I can divide this into 6 parts and then say 1 here is a 6 over 6. So by saying it's dense, I mean if we've got the rational number x and the rational number y, we shall always have another rational number in between the two. That's what we mean by the rational number line being dense. Then let's try to illustrate that. Let's say I go then click 1, 2, 3. Then let's say I've got 2, 6, and 3, 6. If I go to a grade 1 and say, is there any number in between? The grade 1 will say, no. There's nothing. It says in between from 2 go to 3. But really, there are many more numbers there. What we simply need to do, the expansion of numbers, and then for example, any number which I choose here, let's say we choose to expand this by 5. We multiply the numerator by 5, denominator by 5, we'll get 10 over 30. And here we've got 15 over 30. Then you can see that here, numbers, these ones, they mark the ends here. In between here, we've got 11 over 30, 12 over 30, 13 over 30, 14 over 30. So there are many other numbers in between here. So you can go on and say, okay, let's take 12 over 30 and 13 over 30. You can expand that by 2. You will get 24 over 60, and this side get 26 over 60. So now you've got 25 in between. So any number, any two rational numbers I pick, there's one there are many more in between. So that's what we mean by rational numbers are dense. But our point, at the point we came to this, I was saying the number line, as we see, we've seen it, of rational numbers. Not all points are taken by rational numbers. So let's see what are other points representing, if they're not representing rational numbers. So we come to talk about the irrational numbers. Now, irrational here is, we can take it as an opposite to rational. It is actually opposite to rational. When I say something is rational, x is rational, I mean x is a kind of number which is a p over q, with p, q, an integer, and q not equals to 0. So when I say it is irrational, let's say I say y is irrational, I mean y is not equal to some entity of this nature. So y cannot be taken to this entity of this nature. Now, to convince you that there's a point like that, we simply need one interpretation of a number. Let's take 1 as a length of 1 unit up to there. So now we take number as kind of 1 marking some distance from 0 as a reference point to somewhere there. So the same unit is taken from 1 to 2. Now if we do that, then we can draw a triangle like this, which is a right angle triangle. And as you can see here, we can take this distance length and translate it this way, because these numbers are equally spaced. We can also say the distance here from there to there is 1. And then we can draw this triangle in such a way that the distance from here to there again is 1. Then we can appeal to Pythagoras theorem, which when you are given a triangle, a right angle triangle, we all know that if we've got this as A, B, and a C, this side is going to be called little c, this is little a, this is little b. Not recalled, but the length of this side is little b and the a and the c. And you know that c squared is a squared plus b squared, which takes us to that c is the square root of a squared plus b squared. So in that sense, if we take that to this situation here, if we call this length here h, the hypotenuse, what that's going to be? That will be the square root of 1 squared plus 1 squared, because these are the sides a and b. And then this simply gives us the square root of 2. Now, this number is a good example of a number, square root of 2, which can never be put as p over q. I'm not going to go into that a lot, but if you're really interested in mathematics, you enjoy reading and studying mathematics, you can go into books. You'll see very interesting proofs to prove that square root of 2 cannot be expressed as a ratio. So in this case, is an irrational number. So the next thing is to sort of try to see where is its position on the number line. In this case, numbers taken as some kind of a distance. In this case, numbers taken as points which are at a certain distance from the reference point 0. This is what we're going to see now. Okay, let's see this kind of a sketch which I've constructed for you here. Okay, we started with this triangle. We've seen that this distance here is 1. And that distance there is 1. Then by Pythagoras, we get that this is a square root of 2. So all what we need to do to find the position of square root of 2, we simply rotate this circle with the center of rotation there at 0. Then we'll see that this length will lie somewhere there and there, which you can mark that as the square root of 2. If you press your calculator, you will see that it gives you 1, 4 and the decimal numbers there. Please don't understand this thing clearly this way. A calculator will never accommodate the square root of 2. The reason being that square root of 2 is a number which has got infinite decimal places which are not even repeating, and for that reason, if it's infinite number of decimal places, it cannot be accommodated in a calculator or any human-made computer, because all computers have got finite memory. So what we see in a calculator, we can see it to 10 decimal places, whatever number of decimal places, depending on the precision of that calculator. So irrational numbers can only be approximated to a certain number of finite number of decimal places, but otherwise there are numbers which cannot be housed in a calculator except for certain chosen number of decimal places depending on the precision which is needed there. So this basically takes us to numbers like pi. They are examples of numbers which are irrational. Numbers like square root of 3, square root of 5, and so on. And then square root of 3 and square root of 5, I think you can do some experiment like this. You can actually see where you can place them on the number line. So in this case now, what we are saying, this number line which we have here, which was we had the impression that it only contains rational numbers. So it also contains other numbers which are not rational, and those numbers we call them irrational numbers, and we're going to use this symbol for irrational numbers, and we've got examples for such. So examples of such numbers: square root of 2, number e. We're going to talk about that. You can just press on your calculator where you see the function ln. You will see also is associated with number e. If you want, I think maybe is first of all this one, you press it and maybe say e and do power 1. You will see that you get a long decimal number which starts with 2 comma something going that way, which is also an irrational number. That is important. So now the number line is packed with rational numbers and irrational numbers. At this stage of development mathematics, no one has proved whether there are further more points than that. So our understanding that a number line like this is a kind of a continuum which you can draw without lifting a pen, and everywhere where you touch it, there is a number. That number can be either rational or irrational. So now, but what is important is that we see that these numbers, they both live in some kind of one universe, which is this line. So then they form a kind of a unit. From that, what can you say now? These numbers, the rationals and the irrationals, I say they form a kind of a unit on what we call a number line. So which means on the number line we've got a union of the rationals and the irrationals, and then we're not always going to say here we've got the rationals and the irrationals. Then we need to place a new name for this collective which is made of rationals and irrationals, and that is what we call real numbers, whereby real numbers contain these irrationals and these rationals. Then we take this stroke here and they come and put it there. Then we've got what we call the set of real numbers. And then if we were to talk about the picture of these numbers or visualize these numbers, we'll simply draw a straight line and say this is a real number line. Of course, we can put our 0 there as our reference point, our point of departure, and that is very important. So now, having maybe, I hope now we've got a kind of a working understanding of real numbers, all the different sub-number systems, you understand them in relation to this. Then what we have here, basically we have got the natural numbers contained in the whole numbers, contained in the integers, contained in the rationals. So between the rationals and rationals, there's nothing in common, but they both live on this same universe. Then we specifically now say this is a union of rationals and irrationals, and then you got real numbers. And then if I just pick 2 points like this, A, a number, B, another number. If I want to talk about numbers in between there, then we'll talk of a number between A and B. Then we call that an interval of real numbers. In this case, an interval which is not inclusive. In other words, the boundaries A and B are not included. If we want to include them, we write that A less or equal to X, X less or equal to B. Then we've got what we can call a closed interval, and that will be an open interval. Open meaning that it doesn't take the extreme ends of the interval. Then one more thing which is very, very important related to numbers is the following: what we call the absolute value of a number. Now, talking about the absolute value of a number, let's get back to that interpretation of a number as a kind of a point which is at a certain distance from the reference point 0. Now, if we look at 1 here, we would say 1 is our unit. So this is our unit. That's basically the unit which we keep as a standard to place 2, to place 3, to place -1, and then. Now, if we wanted to talk about -3 and 3, and say what is common between these two, 1, we can see that if we put a mirror line at 0, -3 and 3 are mirror images of each other. And if we count the units between the 0 and the -3, and between 0 and 3 is the same. So then, if we were to take this unit as a unit distance, then we can now talk about the distance of -3 and 3 being the same, the distance from 0. So if we want to talk about that, that's when we talk about what we call absolute value of a number. So we would say in this case here, absolute value, I'll use this for a start, absolute value of -3, taking as a number of steps to move from 0 to 3, is the same as the absolute value of 3. And that is 3 units unit distance. So then now we can talk about any number x which is a real number and do exactly the same thing. Conventionally, to say exactly this absolute value of -3 or absolute value of 3, we write it as this way using this bar, and we read it as absolute value of x. So now what we can see here is that when the number is negative, the absolute value is 3, this is positive. And when the number is positive, absolute value is 3, looking like it coincides with the number itself. On the other hand, if we say absolute value of 0, we'll be talking about the distance of 0 from 0. But if we're at 0, we don't make any step to go to 0. In other words, the 0 units we move to get to 0 already at 0, so is 0. So from these two, what we can say absolute value of any number x will be greater or equal to 0. And then now once we've got that, now we can now get a kind of a formula which is standard for defining absolute value of a number. In this case, interpreted as distance from the origin, our reference point 0. So we can say absolute value of x is equals to x for x greater or equals to 0. Now, for this and that, we get that. But then if we now look at now if we check for x less than 0, so what we know is that here this x would have a negative sign, but we want to part from a number which has got a negative sign and get something greater or equal to 0. So then that takes us back to combination of signs, like when we multiply a negative by a negative, then we say the answer would be a positive. So since here we want a non-negative number, we want a number which is greater or equal to 0 for that non-negative number, then which means here for a negative number, for it to be converted to positive, we would need a negative sign. So what we would say here, if x already got a negative sign, then we introduce a negative before that number, then we know that it's going to be greater or equal to 0. Like if we had a minus 3 and introduce a minus sign there, according to this, then we get this equals to 3. Then what we have here is the definition of what we call absolute value of a number. And you must be very, very careful with this. I'll just show you one example why you must be careful with this. You must really practice this, because you need this thing later when you calculate limits of functions which involve absolute value. This is what I mean. Let's suppose with an equation like this. You say absolute value of x plus 1 equals to 3. Now, if you look at this, whatever is inside here, the absolute value, it can be greater or equal to 0, or it can be less than 0. So which means this kind of situation creates us two cases here. Case number 1, if x plus 1 is greater than 0, which means this is what's going to happen. The absolute value will be exactly equals to x. Now it will be exactly equal to what is inside. So what we mean here, we will say x plus 1 would be equals to 3. Then we solve this equation, we get that x is equals to 2. But for case number 2, we should also consider the situation when this is less than 0. So we can now say if x plus 1 is less than 0, which means to make it equal to 3, we then need to multiply it by negative 1, which will say x plus 1 is equals to 3. Then we can solve this equation. Here we get minus x minus 1 equals to 3. Solving this, adding plus 1 on both sides, we'll get minus x equals to 4, which will simply say now x equals to minus 4. And if we check, you will see that these two numbers, they satisfy the equation. So let's suppose x was 2. So if you substitute here by 2, you get 2 plus 1, 3. Absolute value of 3 is 3. If x was minus 4, we'll come here and say absolute value of minus 4 plus 1. Getting within these bars here, you say minus 4 plus 1, you get minus 3. And the absolute value of minus 3 equals to 3. That is very important to master that. And this also can take you to inequalities. For example, there are two things which I want to show you here. Let's get to the number line here. Let's suppose with something like this, x, absolute value of x less than 2. You must see that when you say absolute value less than 2, it means that to get to x, you must move number of units less than 2, which means from here you can't get to 2. So we're talking about that. But also to get to be less than 2, for a number to have an absolute value less than 2, it also counts the numbers which are from here this way and not getting to 2. So this simply translates to x's between 2 and minus 2. And then the opposite of it will be absolute value of x greater than 2. I want you to imagine what would you do if it was less or equal here and here greater or equal. So obviously then for this greater than 2, then you'll be looking at numbers which are more than 2 away from 0, which means then you're talking about numbers this side. But those are not all only the numbers. These ones also, this side, they are also at a distance greater than 2. So in other words, for this one, you get a kind of 2 half lines, which one starts from 2 going to the right and the other one starts from minus 1 going to the left. But this one, you get an interval which starts from minus 2 to 2. It could be open or it could be closed. Closed when you include the equal sign there and there. That would be less or equal and that. So that's what I want. That's where I want to get you to. So the most important thing here is to have a good understanding of what we mean by real numbers and how we can visualize them on a number line. Give a good idea of what we mean by an interval, when it's open, when it's closed, and also important, understand what we mean by the absolute value. The next thing we get as a bonus from having a real number line is the following, what we call the XY system of coordinates, whereby we've got practically a real number line running horizontally, and we call it X there, and another real number line running vertical there, and we call the Y axis. So here we've got the two axes, which are X and Y axis, horizontally and vertical. So what is important with this is that we're going to use this as a very good instrument for plotting. You know already, we use this as a very good instrument for plotting our functions, the graphs of our functions, because graphs are very, very good things which can give us an easy interpretation of what the function really is happening, whether it's growing or it's decreasing and so on. We get it from a graph. So what is important here that you must know how to represent a point, like plotting a point. Like for example, if I count here 0, 1, 2, 3 and 1 this way, I would have a point there which I can say its coordinates are 3, 1, whereby 3 stands for x coordinate and the y stands for the y coordinate, and these are called the ordered pairs. They are ordered pairs because if we have 3, 1 as a point, and we've got 1, 3, those are two different points. So the order is very, very important here. So this 1, 3 will be a point like 1 here, then count 3 going there. That will be a point there. So when you name these points, when you plot them, you must always understand that the order is very important. So I think this comes as a bonus once we've got the set of real numbers and we understand what's happening there. Then we can do all sorts of things now, plot our graphs, do even our trigonometry, do our analytic geometry, and so on, so on. So at this point, I'm leaving you with this kind of a recap of the number system and what we can get from number system like this, issues on the absolute value, representing intervals on the number line, and so on. At this point, I would like to say thank you for listening. My name is Charles Msipa.